Okay, good afternoon or good morning, everyone. It's Deb Sparks from the Centre of Excellence for Prescribed Birding here. I'm just going to introduce Jason Sharples and Valerie Densmore. Jason's from the University of New South Wales, and he's going to give some scientific reasoning as to why we might experience some unexpected fire behaviour known as vorticity lateral spread. And Valerie from the Department of Biodiversity and Conservation, WA, is going to present on an example of where they did experience some unexpected fire behaviour leading to some pyroCb clouds. So with that, Jason, I will just hand over to you.
All right. Thanks, Deb. Hopefully everyone can hear me.
Yes, I can hear you.
All right, good. Okay, yeah, so what I plan to do is just give a bit of a brief history of the research that's been done around this particular phenomenon called Vorticity-driven Lateral Spread, or VLS, and then just point at a few examples where it may have caused things to sort of become pear-shaped in a couple of prescribed burning cases. So going right back, it seems that the very first, I guess, bit of research which hinted at this kind of effect was actually done by Clive Countryman back in the 60s and 70s, and he's got his little 1971 report here, Firewells, Why, When and Where. And in that report, if you look into it, he's got this little bit where he talks about firewells. First of all, he talks about how they enhance the spotting process. Okay, you get firewells, you get very strong winds which tear off bits of bark and other bits of vegetation and send them up into the whirl, loft them further than they might ordinarily go. But the other thing of interest is that he sort of notes that they're more prevalent, firewells are more prevalent on lee-facing slopes. And you sort of see the graphic there, I hope, where you've got the thermal wind from the fire burning on a lee slope interacting with the ambient wind coming over the top of the ridge, and sort of this merging of the two flows creates these firewells with high frequency. So that was kind of interesting to see that back in the literature. But really, I mean, Countryman doesn't seem to have really, I guess, appreciated the full consequences that this sort of effect can have. So nothing really happened in the interim up until about 2003 when we had the fires here in Canberra. And looking at those fires, Rick McRae sort of noted multiple instances of this atypical lateral spread. Okay, so where the fire was actually spreading across the wind instead of with the wind. And these instances were quite often associated with downwind infill. Okay, so I'll talk about that in a minute. But here's a picture, sort of pictures that Rick was looking at. So here's two overlapping line scans about 15 minutes apart of one of the bits of the Canberra fire. And the interesting thing is if you have a look, just got to remember how to get the little red dot up again. Okay.
Press the pencil.
Yep, okay, I've got it. So the interesting thing is to look in these regions here, 15 minutes apart. You can see that despite the fact that the wind's sort of coming out of the northwest, you've got this development of the fire sort of moving towards the northeast. And in this instance here, you can see that that lateral spread of the fire has this big yellow blob of sort of active fire. Downwind of it, you can see little spot fires forming laterally again. This is what I'm talking about when I say the downwind infill. So all the areas downwind of where that lateral spread has occurred is sort of filled in quite rapidly and is burning. So these observations really prompted us to start having a bit more of a look at this effect, and that took us into the Bushfire project, which was part of the original Bushfire CRC program of research, Bushfire Risk Project. That was run by Rick McRae and Rod Webber, and that's where I sort of entered into the research sphere as well. So what we were able to do as part of that research was really look at this particular sort of fire behaviour and tie down some, I guess, distinct characteristics. So these were things like you always had a distinct kink on the upwind edge of the fire. Okay, and you sort of saw that on those last slides. you sort of had this, this kink where the fire would start spreading laterally. Fire spread in a direction nearly perpendicular to the prevailing wind. That's the lateralness of it. The upwind edge of the lateral spread always seemed to align with a break in topographic slope, okay, when the fire was burning on the lee slope. Not every lee slope. It only occurred on slopes that were sufficiently steep and sufficiently lee facing. I'll talk about that a bit more later on. And one of the other diagnostic features we saw was that you always had this dark sort of cauliflower textured smoke on the advancing flank of where the fire was spreading laterally. So I guess the next sort of chapter in the saga was to really start, well, okay, I'll just give you an idea of what I'm talking about here. So here's an example of the effects. This is on the Blue Range and the Canberra fires. So what you can see, you've got the wind pushing the smoke that way. The fire has really come around the edge of a spur here and is now spreading in that direction. So that's the lateral spread. And the dark smoke that I'm talking about is, you can see it on the edge there. So this dark smoke is really indicative of incomplete combustion and probably resulting from very rapid combustion. The oxygen is being used up a lot more quickly than it can be supplied. Although I have to say we're still in the process of fully understanding why that dark smoke occurs in this process. So we don't really understand that yet, but that's kind of the thoughts around why it's happening. In 2010, I got some money from the Australian Academy of Science to go over and work with Domingos Viegas in his lab in Portugal, really well-known fire lab over there. And so what we were able to do there was provide the first experimental verification of this effect. So small-scale laboratory, this is only a metre or so across here. You can see the big fans pushing the air out over this lee slope, and we've got a fire which has been lit on the lee slope. And if we watch how that fire develops, then you find that started here, it burns up, and as soon as it hits the ridge line, it starts spreading across in this sort of finger of fire like we saw in those line scans before. Interesting to note that even in the laboratory experiments, you get that dark smoke on the advancing flank. You can see it there. And if you saw the video of this, you can actually see little spot fires forming down here as well, which will be important for later on. So this really gave us an idea of, okay, this is a real thing. We can verify it happens experimentally, and the experiments kind of look a bit like what we're seeing in the actual wildfire observation from the light scans. So the next phase of the research was to go away and say, well, okay, we've looked at laboratory scale demonstrations of it. We can't really go out into the landscape and do full, kilometre scale experimental burns under the sorts of conditions where this is likely to happen. For obvious reasons. So the best option we have then is to really try and model this at landscape scales using numerical models. So this was the aim of some research that we got funded through the Australian Research Council, was to go away, look at some coupled fire atmosphere models and try and see if we could understand this process a bit better. So the nice thing about the coupled models is you can actually run them as coupled models so that the atmosphere and the fire are interacting with each other. Or you can run them in an uncoupled mode where the fire reacts to the atmosphere or the winds, but the fire doesn't feed back onto the atmosphere, okay? So if you turn the feedback off, then what you actually get is something like this. So this is a simulation over 2 hours. This is the fire at 60 minutes, 90 minutes, and 120 minutes. You can see it's being lit with this little cross-hatched bit here on the lee slope. The wind is coming from the left. This is the top of your ridge here, the dark line. And you can see what happens when the feedback is turned off. Just simply burns back up the slope and spreads out along the flank that you would normally expect a fire to do. Interesting thing though is when you turn the feedback on, so now the fire is feeding back into the atmosphere, telling the atmosphere what to do as well, you get a very different result. Okay, and so you can see now that with feedback on, not only does the fire reach up the top of the slope faster, but once it does that, it starts to spread laterally, just like we saw in the line scans and also in the experiments. So the fact that we get this effect only when the feedback's turned on is really telling us that what we're dealing with is a mode of dynamic fire propagation, which is driven by a three-way interaction between the fire, the wind, and the terrain. Okay, so the wind and the terrain are important, but the fire also needs to be involved for this thing to kick in. And that's just to show you that what we're getting out of the model does produce patterns of spread very similar to what we're seeing in the laboratory. So there is this physical effect here, which seems to operate over a range of scales. So here we've got a factor of, or an order of magnitude difference of 3. So this is metre scale, this is kilometre scale, you're getting very similar looking things. So the process, whatever's driving it, seems to be able to scale over these different spatial scales. The real interesting thing, or the real useful thing about the models, is it actually allows us to really hone in on what's driving it. And so this little spaghetti diagram here, these are wind tendrils. The red shading is the fire. If you can look carefully, if the fire started down here, it's spread up, and you can see there's actually red under here where the fire is spreading laterally, also over here. But the main thing to notice is that where that lateral spread is occurring is you've got these fire whirls. So that brings us back to countrymen saying, well, these fire whirls are actually, naturally suited to be developing on lee slopes. But what's happening here is that not only are they developing, but they're carrying the fire laterally with them. And this is where we really got the name that we give this thing, or the name we're using now, Vorticity-driven Lateral Spread, just to acknowledge that the lateral spread is actually driven by this pyrogenic vorticity. It's the whirliness of the wind driven by the fire, which is what's causing the lateral spread ultimately. At least that's what the model says. We hadn't really seen the vorticity in the experiments that we did in Portugal, but I had a brief visit to the fire lab in Missoula in the US, and we were able to create these fires without smoke and very clean fires. And sure enough, you do see the vorticity coming out of these fires. That was a nice little confirmation of what we're seeing in the model, again, at a different scale, but very similar effect. The other interesting thing we saw from these fires that we lit was, despite the fact that we only put fuel, okay, the fuel was just alcohol, but we only painted the alcohol on in between these two dashed lines. So despite the fact that that was the only thing that could burn, you were still getting fire out where there was no fuel. And that, for me, as a firefighter, always makes me think, well, if you're on a lee slope and you've got some sort of spot over and you're cutting a trail down around it with a Rayco, if this sort of effect kicks in, then you've got the potential for the fire to jump across that mineral earth line quite substantially by going by that. You're pressing the wrong button. All right, so that sort of brings us up to recent times. We've also continued to consider this form of fire behaviour as part of the more recent Bushfire and Natural Hazard CRC spot fire project that we're involved in. So this is between UNSW and James Hilton and Andrew Sullivan from CSIRO and Data 61. And what we've been doing there is really going back and looking at the models and saying, well, it's all very good, that we can have these models which can reproduce the effect. Okay, and up until about 12, 18 months ago, the only models which would produce these effects were these coupled models. So here's the one you saw before. The thing to note, though, with the coupled models is that when we run this simulation, which lasts for 2 hours, in terms of computation time or simulation time, we're really looking at about 12 hours on the supercomputer at the National Computational Infrastructure. Okay, so having a computer run for 12 hours to give us what the fire is going to do in 2 hours isn't really going to be operationally that useful. We really need to bring those simulation times down. So that's what we've been trying to do. And just recently we've had some success in that. So this is a two-dimensional near-field model. So this is using the pyrogenic potential model, which some of you may have heard of, simulating VLS in the Spark platform, CSIRO Spark. The nice thing, instead of taking 12 hours, you can do it in about 10 seconds, just on an ordinary desktop or laptop computer. So that's a speed up in computation of about, a factor of about 4,000. Just to convince you that it's a useful development, if you actually look at how the 2D very fast simulation compares to the full bells and whistles coupled simulation, it's pretty good. Okay, a lot of bits here that we're missing. We believe this is due to turbulence, but the next year and a half that the project's got to run, we'll be looking at refining it to be able to try and pick up some of these effects. But I think, for the time being, that's a pretty good win. 4,000, factor of 4,000 speed up in simulation. We can start to build these things into into operational models now. All right, so just by way of summary, VLS, Vorticity-driven Lateral Spread, has been the subject of a fairly extensive program of research over the last 10 or 15 years. We've determined that it is a real physical effect. Okay, it's real. It's driven by physics. It will happen whenever the physics is suitable for it happening. Okay. It's been observed in wildfires around the globe. It's been observed in laboratory experiments and computer simulations, which all give very consistent renderings of what's happening. It's a mode of dynamic fire behaviour, which means it's not always going to obey the traditional rules set out for fire behaviour. Okay, there's extra elements go into driving it. Indeed, if we look at the rate of spread associated with VLS, it's rapid, okay, probably faster than some headfire rates of spread, but in a direction contrary to where you expect it to be going traditionally. Okay, so 90 degrees to the wind instead of with the wind. Two important things is that to realise that it's subject to threshold behaviour. Okay, and I'll show a slide next to explain that a bit more. But the upshot of that is that it can exhibit very abrupt onset. Okay, so environmental conditions only need to change a little bit for that threshold to be crossed and for the effect to switch on or off. It's also one of the key contributors to what we refer to as deep flaming, which has been associated with the development of towering pyrocumulus and pyroCb storms, as Val will talk about in a little bit. But just in terms of the thresholds, there's a bunch of things which really have to happen, or a number of ducks which have to line up, if you want to think of it that way, for VLS to occur. So the lee slope angle, okay, the inclination of the lee slope has to be right. By that we mean it has to be greater than about 20 degrees, okay, so sufficiently steep. Also has to be sufficiently lee facing. The aspect of the lee slope has to align with the wind direction to a certain degree, typically within about 40 degrees of the wind direction. I'll show an example of that in a minute. The wind speed has to be sufficiently strong, okay, greater than about 15, 20 kilometres an hour. These first three conditions are really talking about conditions which are necessary for the winds to separate from the surface in the lee of the ridge. Fuel type and fuel load, well, it's generally not going to happen in light grasses. You're really talking about heavier fuels, mainly forest, and really that's to make sure that we're getting a plume with enough strength that it can be, you can stand up to the wind coming over the top of the ridge. Okay, so the plume has to be strong enough to provide some interaction. The moisture content of the fuels is really for the spotting component, which I'll also talk about in a sec, but really we're talking about very dry fuels which are conducive to very efficient spotting. Why is that important? Well, it's because when we talk about deep flaming associated with VLS, it's actually a two-stage process. So if I have a hill like this with some wind going over it and I've got an ignition on the lee slope just there, the little star, then the way we get deep flaming out of that happens in two stages. The first stage is just as we've seen in the experiments and the simulation. The fire burns up the slope, hits the ridge, and then starts spreading laterally. Okay, so that's stage one. The second stage is really what happens after that is because along here, as Countryman said, this is all very prone to having these firewalls occur. We've seen the vorticity in the simulations. What that means is it's going to be tearing off a lot of embers. So we have enhanced ember production here, and so there's unburnt fuel downwind of that. So all the embers are now flying off from that lateral spread region downwind, starting spot fires, and this can be fairly dense spotting, and what happens is all those spot fires will start to coalesce, and very rapidly you end up with the ball of fire, okay, quasi-simultaneous active flaming, okay, over a large area. And by a large area, we're talking several hundred hectares. So just a couple of examples to finish off on how this impacts on prescribed burning activities. This is a picture of a hazard reduction burn. You can see it's in reasonably rugged terrain. Initially, the hazard reduction burn was down in this region, but what happened on a particular day was back in March 2018, I believe, we got some strong fern flows developing, and that pushed the fire over across the containment lines. It got onto this lee slope, and you can see it's actually spread across the slope. So again, those familiar things, the wind going that way, and the spread on the lee slope spreading laterally like that. And you can even see the darker smoke on the advancing flank there. Produced multiple spot fires, as we can see in this picture. It's just a different view, the wind going that way, the spread, you can see the kink in the fire perimeter there coming towards us, and you can see all the spot fires which are forming downwind of that lateral spread region. Okay, so that's clearly not what you want to happen when you're conducting a hazard reduction burn. It can also cause problems when you're doing tactical backburning, which I also class as a form of prescribed burning. And here you can see a fire. This is the main fire, which was trying to be stopped. You can see they've put in a backburn along the fire trail here. Along this part of the backburn, things have gone well, and the fire is spreading towards the main fire that's trying to be stopped. But what's happened is that when you look at that aspect there, the difference between the aspect and the wind direction is about 52 degrees. Okay, so that's bigger than the 40 degrees or thereabouts I was saying before is the threshold. What happens though is you move around the fire trail, the aspect changes. So as we move around onto this part, then the wind and the aspect are lining up, only about a 17 degrees difference there. So that's within the 40 degree threshold. And you can see now that the fire has developed in a completely different way. It's not going back towards the fire. It's basically become the fire and it's become the main cause of concern, spotting and so on. Just another quick example of more recent fire. So you can see here, these are two line scans about an hour apart. Here we have a fire being ignited about 20 past 1. It was ignited here, and as you can see, it's actually spreading up the slope away from the wind. Just there, I think if I can show you, okay, so that's where the fire was. That's the corresponding point 57 minutes later. And so you can see what's happened in those 57 minutes is the fire has actually spread, aligning with those ridge lines there, at about 1.5 kilometres across the wind. Okay, again, we have the downwind infill due to spotting. And if you calculate the rates of growth in terms of the fire area, we're talking about, aerial growth rates of up around 500 hectares per hour. So that's getting up to sort of, Black Saturday growth rates, things like, the Bunyip fire was up around 900 hectares. Kilmore was about 250 hectares per hour, so fairly significant growth rates. That's just a picture of what the fire looked like at about the same time as that second line scan was taken. And again, not something you want to see as an outcome of any prescribed burning activity. So that's really all I had to say. I'm going to hand over to Val now, and she'll go into a bit more detail in a particular prescribed burn.
Thanks, Jason. Can everyone hear me all right? Can you hear me all right? Good.
Yes, you could, Valerie.
Right. So, thanks for sticking around. Good morning or afternoon, depending on where you are. So I actually would like to discuss a prescribed burn that was conducted in Western Australia that actually produced something of a bit of a vertical overachievement, I suppose, in that it produced two Pyrocumulonimbus clouds. This burn was conducted in November of 2017 in the southwest of WA. Just to give you a bit of background about burning in WA, southwest WA has a Mediterranean climate, so we've got generally cool, wet winters and warm, dry summers. It's a biodiversity hotspot, so we've got quite a few different vegetation types, and they can mix together within a single burn. So we can have closed and open forests, including both dry and wet sclerophyll forests, woodlands, shrublands, and heath. the Land Management Agency, which is currently called Department of Biodiversity, Conservation and Attractions, has actually been conducting prescribed burns in the Southwest WA forests and woodlands for well over 60 years. And we've been conducting burns with aerial incendiaries for over 50 years. So, and they have averaged, say, in the last 30 years, between 100 to 200,000 hectares per year. So there's a fair amount of experience with prescribing and conducting prescribed burns, which makes this particular case quite interesting for us. So Table Hill, or Franklin 053, was a prescribed burn. It was conducted in open forest and unexpectedly caused the eruption of 2 Pyrocumulonimbus clouds, or pyroCbs, during edging operations on the 8th of November. And there's actually a little video showing the blow-up of the first pyroCb. I'll start it. See if this works, hopefully. It's just a loop of satellite imagery. Oh, there we go. Let's see. It may not work. It doesn't seem like it wants to.
I've got it working at my end here, Val.
Do you? Okay. Yeah, it's just a visual of the pyroCb forming. So there we go. I'll let it play a little bit more. So really, with prescribed burning, it's intended to really mitigate rather than create extreme fire behaviors. So the production of 2 pyroCbs at one of our burns prompted a review, which I conducted, to identify some of the key contributing factors so we could better understand some drivers of the coupled fire-atmospheric interactions, but also to identify any actions or decisions that can be changed in the future to prevent future blow-up events at prescribed burns. Go back to the slides. So at first glance, there were several factors that carried risk in this burn, but none seemed especially hazardous on their own. The timing of the burn was constrained to mid-spring because there was a declared rare orchid within the burn parameters, so that these can only be burned after a certain time. And there were also riparian areas where we needed to retain a moisture differential for wildlife corridors. So if you can see in the top right image, the burn contained 2 cells divided by an internal road. And this had mistakenly not really been cleared for quite a while and ended up being somewhat marginally suitable as a fire break, though that was unknown when the burn was begun by some of the management. The burn prescription classified the vegetation type as heath and southern jarrah forest. And southern jarrah forest has a moderately tall and dense understory that retains moisture longer than the actual fuel types within the burn, which were predominantly open jarrah forest and woodland with some heath and sedgeland areas. In addition, the site had been burned around 9 years before, but that burn was fairly patchy because a bushfire had occurred 5 years prior. So the classified fuel age was somewhat misleading. Jarrah forest at 9 years old is well within the range of typical for conducting burns, but once you get to 14-year-old jarrah forest, it's expected this fuel age is going to elevate fire behavior. However, it might be hard to see in the lowest image on the right, lowest map on the right. The surrounding fuels were relatively young. They vary between about 1 and 5 years old. So this considerably limited the risk that the burn would be able to escape. In addition, the smaller western cell had been edged and a core ignition completed during the preceding 2 days before the blow-up event, and no significant incidents had really occurred, giving a fair bit of confidence, I suppose, to continue with the eastern cell. So to walk this back a little bit in case there are listeners who aren't very familiar with pyrocumulonimbus or pyroCbs, I think it's probably worth discussing a little bit what a pyroCb is and what can cause them to occur. So a pyroCb, it occurs when a smoke plume essentially punches through the stratosphere and produces what is essentially a thunderstorm. It can include lightning, downdrafts, and quite erratic and elevated fire behavior, so dangerous for personnel on a fire line and for maintaining control of a fire. PyroCbs remain somewhat difficult to predict, but it's fairly well accepted that they require an unstable atmosphere and sufficient lift to permit the smoke plume to penetrate the stratosphere. So this lift usually will come from a large heat source, like a large fire, or significantly elevated fire behavior, but the lift can also get a bit of a boost from slopes or other topographic features. In addition, usually light winds are needed so the plume isn't forced to lay over as it does in some stronger winds. Atmospheric indicators present at all or nearly all PyroCb events include a low level of free convection. So this reduces the distance that the plume has to rise due to the fire before it will rise unaided or is enhanced by atmospheric lift. And also an inverted V on the aerological diagram or thermodynamic sounding. So, and I've included an example of this inverted V on a thermodynamic sounding. It basically, what that indicates is that you have a dry lower atmosphere that's overlain by a moist middle layer, and this moist middle layer really helps enhance lift. So if we look at atmospheric conditions on the 8th of November, when the PyroCb occurred, they do fit the necessary profile for the PyroCb to occur. So an inverted V is visible on the Perth sounding, which was taken approximately 250 kilometers northwest of the burn. So that's, let's see, that's here. So this is visible on the Perth sounding at 8 p.m. on the evening before, and it's maintained throughout the day on the 8th, both in the Perth morning and evening soundings and also in the Albany sounding, which would have been taken east of the burn. So this really covers an area that the burn would have occurred in, that we had this inverted V on the aerological diagram. Let's see. The level of free convection measured at Perth dropped to basically it was not applicable in the morning on the 7th, the day before, to in the evening it dropped to around 35, just above 3,500 meters, and was below 4,500 meters on the day of the 8th. So this also would have decreased the amount of lift necessary. I've also included a picture of some hodographs. So hodographs show wind speed and direction in the ascending air column. And on the preceding day, on the 7th of November, the Perth hodograph has this mid-level wind shear. You can kind of see it there, which would have helped to bend over the smoke column. But on the 8th of November, I've shown both a cross-section and a top-down view with the red arrow showing where it starts, I suppose. There's what seems to be a rotational pattern, suggesting that there was probably some pre-existing vorticity in the atmosphere that certainly would have enhanced air buoyancy. In terms of the surface weather, on the 8th, the forecast was for a maximum temperature of 31 degrees, a minimum of RH 31%, and warm, dry, northerly to easterly winds at between 15 to 25 kilometers an hour. But the actual conditions that occurred included an unforecast southerly wind change and considerably lower humidity and dew points than what was predicted. And I've highlighted where there's quite a strong difference in the red text there. We think this is probably due to a frontal system that was forecast to produce a thunderstorm during the early evening. And it's worth noting that this thunderstorm had been forecast the day before, really with sufficient warning to have not begun burning the eastern cell, but I'll go into why we did go into burning that eastern cell later. Satellite imagery suggests that the first PyroCb erupted coincidentally with the passage of a cloud band linked to the frontal system, and I've indicated that here with this blue arrow. So you can see this cloud band passing over the burn. That's at about 10 past 12. And then the pyroCb erupting, that's indicated by these white arrows. And it actually remains linked, if you can see this. It remains linked to this cloud band until the arrival of a true thunderstorm, shown here with the yellow arrows, or it's got a wider appearance than the gray smoke associated with the pyroCb. So it remains linked until this true cumulonimbus arrived sometime after 1600 hours. Okay, so in terms of what promoted the lift to occur, the atmospheric conditions probably were quite suitable to promote a pyroCb, but we still needed to have sufficient lift. And as I mentioned before, this usually comes from a large heat source, but it can be enhanced by topography. And this map here, this kind of green map, is made to try and illustrate the complex topography that occurred within this burn cell. So what you have is multiple discrete hills around linked river valleys. And these river valleys, we believe, probably channeled wind at different speeds and directions to the prevailing conditions. The slopes of these hills, for the most part, averaged around 10 degrees, which is enough to potentially double the rate of spread of fire traveling upslope. The hilltops as well were only around 200 meters across, and this is a short enough distance to really allow turbulence and spotting to occur over onto the side of the slopes, so we potentially had additional uphill fire runs. The available fuel loads had been measured as typical for around 9-year-old open jarrah forest, but the fine fuel moisture had dried from 12% when the burn was started on the 6th to around 7% moisture on the 8th when the pyroCbs occurred. And so the WA fire behavior tables, also known as the Red Book, suggest that this level of dryness can actually multiply rates of spread by a factor of about 1.8. So when you combine the effects of slope and fuel dryness, we could have probably amplified the predicted rates of spread from 48 to about 173 meters an hour. Okay, so for ignition patterns, this is really quite interesting. The ignitions introduced into this cell were actually limited to edging on the day, and I've depicted this, the edging that was introduced in this map in an orange color. So the 10-kilometer southern boundary was actually edged the evening before on the 7th and had achieved over 200 meters depth by 8 o'clock on the morning of the 8th. So this decision to edge the southern boundary was based on finding the internal road between the two cells probably insufficient to hold the burn that has occurred in the western cell. And also the surrounding fuels were considered young enough that they probably would prevent any risk of fire escape. So on the 8th, the northern boundary was divided into eastern and western sectors, and the northwestern sector included a Department of Water gauging station, which is shown kind of as a blue dot on that map. It's around 750 meters south of the northern boundary. So the decision was made to edge around this gauging station, and that edging began around the same time the edging began on the northeast sector. Around 45 minutes later, edging was begun on the northwest sector. So all of the edging was introduced from west to east, initially using spots that were spaced about 100 meters apart. But what the fire managers were finding was that these spots were joining up, producing junction zones, and then actually fire was running back out to the boundary. So they changed the method of ignition to short continuous lines to prevent the formation of junction zones. The fire behavior was a bit elevated for what we consider normal for prescribed burn in this vegetation type. We had flame heights between 1 and 4 meters tall, and the rates of spread were between 80 and 150 meters an hour. Around 12:15, 2 spots were introduced at the southeast corner, but this was really rapidly halted because there were fears that an unforecast southerly sea breeze might actually impact the burn. So around midday, crews reported hearing quite a loud thunderclap, and satellite imagery showed that the first pyroCb erupted around 12:10. It's important to note that only a portion of the edging that I've depicted here had been introduced at this time because lighting continued for another 5 to 6 hours. And nearly all of this cell, which was 7,953 hectares, burned out within 8 hours with this edging. So the question was, how did this limited amount of edging spread over such a proportionally large area? So using quite a bit of field analysis, I looked at freeze direction and scorch heights to reconstruct the potential path of fire spread. So I'll take you through the various sectors and ignition points to talk you through how I believe the fire spread. So with the gauging station, it was against a prevailing wind direction that we had northerly winds, but fire spread upslope from the gauging station at relatively high intensity. So we have full scorch within 20 to 30 meters of the ignition points. I've tried to show some of that with these white arrows here with the epicormic growth that's occurring on the jarrah trees indicating full scorch. It's likely that a combination of the slope and potentially lee-side turbulence and junction zones forming with edging from the northern boundary probably helped to elevate this fire behavior and produce this full scorch in this area. So if we look at the northwest sector, this really corresponds to what Jason was talking about. The vegetation freeze patterns that I've tried to show here in these photographs was showing that the fire was spreading laterally across the lee slope. And this is perpendicular to what was somewhat northeasterly winds. So we had quite rapid spread laterally across the slope on a lee slope. So this really seemed to me to illustrate VLS that Jason was talking about. I'm not sure if the slope met the criteria of 20 degrees or more, but I should go back and look at that now that I've heard Jason's talk. So I took infrared imagery from the Himawari 8 satellite, and so you've got 2 images there spaced 10 minutes apart, and what it shows is that you have quite a rapid increase in fire intensity on the northwest boundary beginning around 15 minutes after the edging was commenced in that northwest sector. So what we did have was the lateral spread of fire and a very rapid lateral spread that helped to produce deep flaming that I think helped provoke that pyroCb. So from the northeast sector, edging introduced there actually was begun in a river valley that was downstream of the gauging station. And I've tried to show this river valley with this white circle here on these maps. The vegetation freeze indicated that the fire actually channeled up this valley towards the lighting around the gauging station and the northwest sector. And the infrared imagery, again from Himawari 8, suggests this began occurring about 30 minutes before the first pyroCb erupted. So we had rapid juncture of fire from the gauging station and the northwest and northeast sectors. This would have produced quite a large area light, possibly extreme fire behavior. And some evidence of that extreme fire behavior included both the full scorch that I showed you in the forest regions, but also in the sedgelands, we had cumulative freeze directions actually in multiple places that looked like vortices had actually occurred. So instead of the freeze all being in one direction, it was actually spread out from a center point, suggesting that we had localized vorticities in the sedgelands. From the southeast corner, the 2 spots that were introduced around 12:15 appeared to produce quite a significant fire run in a northwesterly direction that began around 12:50 and traveled actually about 8 kilometers in 1.5 hours, so quite a rapid fire spread, according to the infrared imagery. So you might be able to see this green line on this map, and this map is actually a differenced normalized burn ratio. So this green line corresponded to vegetation freeze patterns that suggested that this was actually the flank of the fire that was running from the ignitions introduced into the southeast corner. And this flank eventually turned into a head fire when we had a southerly wind change later in the day. It's notably the DNBR suggests that the edging from the southern boundary actually produced very little in the way of a fire run. There was concerns on the day that the edging from the southern boundary would actually produce a significant fire run up to the north, and that's why the northern edging was done. But in hindsight, possibly that edging didn't need to be introduced. So the first pyroCb reached its maximal height around 1512 and then dissipated around 45 minutes later. Okay, so with a southerly wind change that was unforecast, a sea breeze had been detected along the coast around midday, and it reached the southern boundary of the burn around 1300 hours. And I've put a little timeline there on the bottom left, showing winds that were reported at the southern and northern boundary, and also at an automatic weather station that was located around, I think it's around 5 kilometers north of the northern boundary, to help illustrate the timing of the southerly wind change, but also the variability in wind direction, and the really erratic wind direction that was occurring during this burn. So this southerly wind change did appear to turn that flank fire, as I mentioned before, into a head fire around 1650, and this is just prior to the eruption of the second pyroCb. Then the wind ended up turning southwesterly around 1800 hours, and we started getting multiple hopovers over the eastern boundary. This led to resources being shifted to this boundary to extinguish the hopovers and light a line of fire up the boundary as a counteractive measure. Fortunately, the fuels on the other side of that boundary were only 5-year-old, and they didn't really carry fire well, so none of the hopovers developed into a significant fire escape. However, the burn also ran out to sections of the northern boundary that remained unedged, and there was a crew on that northern boundary that actually ended up having to activate the deluge system to cool their trucks. Fortunately, the fuels on the other side of them were only 1-year-old, so we averted a potential quite serious situation. And these fuels, as well as the fuels across from the eastern boundary, were able to withstand the extreme fire behavior. So the fire did actually cross that boundary and run for about 30 meters before it self-extinguished. Okay, so to kind of look at the fire spread using a model, James Hilton at the CSIRO kindly modeled the pattern of fire spread at the Table Hill using SPARC, the model that Jason mentioned before. So this incorporated surface weather but not atmospheric conditions. And the isochrones that SPARC produced actually reiterated what I predicted using the vegetation freeze and the infrared imagery, showing quite a good result, actually. The only thing was that SPARC predicted the burn would have been completed after 24 hours rather than 8. And I think this really illustrates the importance of atmospheric interactions to elevate fire behavior. So to examine the atmospheric potential, Kevin Torrey at the BOM analyzed the pyroCb firepower threshold, or PFT, at 6-hour intervals over the course of the burn. And so Kevin has actually given a webinar before for the Center of Excellence about the PFT. So for anyone who hasn't watched that, I'd recommend watching that recording, and he gives quite a bit more detail about his methods there. What he found was that in the morning, that about 50 to 100 gigawatts of energy was needed to trigger a pyroCb. but at 1400 hours, this dropped to between 0 and 50 gigawatts. I'm probably not 0 gigawatts, but quite a low amount of energy was necessary. Low heat threshold was necessary to produce a pyroCb. So in some ways, it seems that the conditions at this burn resembled something of a perfect storm. So to kind of summarize, the reconstruction analysis indicated the key factors were ignition patterns in a complex topography, particularly unstable atmosphere, which included relatively low wind speeds, a low level of free convection, pre-existing vorticity that probably increased air buoyancy. So it's likely that the dry fuels further promoted the rapid rates of spread that was observed on the satellite imagery. The western cell actually contained multiple hills similar to the eastern cell, but the western cell didn't produce similar levels of extreme fire behavior. So again, this highlights the central role of an unstable atmosphere and approaching frontal system that possibly acted as a trigger for the first pyroCb. However, lighting patterns were more complex in the eastern cell, and this raised questions for our department whether conducting the burn over a longer time period that maybe used some moisture differentials between valleys and the ridgetops would have helped prevent some of those upslope fire runs. So really all prescribed burns will carry elements of risk, and this is whether or not the prescribed burns are conducted or not. So I guess what the take-home message is from this burn in particular is that the importance of observing when burns contain risk multipliers and really giving due consideration to the possible consequences when risk multipliers are layered within a single burn. I also wanted to, this analysis really couldn't have happened without significant contributions from several people, so I've listed them there and want to say thanks for their help, and thanks for listening, and I'm happy to take any questions.
Thanks, Jason, and thanks, Valerie. I think it's really great that as an agency you're able to share your learnings from when something went wrong. Sometimes people can be a little bit hesitant to do that, so thank you very much for that. I'll just open the lines up for questions.
The conference is now in conversation mode. All participants are now unmuted.
Okay, does anyone have any questions for Jason or Valerie?
I have a question for Valerie.
Go ahead.
So, Valerie, Jason, when you talk about your slopes, how were they measured? Were they from a DEM or actually measured in the field?
No, they were measured from a DEM.
Okay, and what was the resolution of the DEM?
What was the resolution of the DEM? I think it's a 10-meter resolution.
10 meter. Okay. All right. It's just that when I was talking about the sort of the 20-degree threshold slope, that's actual slope. You need to sort of take into account that when you have a DEM, you're not going to be measuring the actual slope exactly. It'll be a bit less depending on how smooth.
Right. Yeah.
That's something we're actually working with the CRC to produce a product which will take that into account.
Okay, any other questions for Valerie or Jason?
Yeah, I've got one for Jason.
Go on.
Yep.
Yeah, Jason, just curious, when they talk about the vortices developing, is it, in this case, only ever one kind of, in the modelling I saw that it was only one vortice kind of on the flanks of the fire as it was moving upslope forming? Is it the one, or can multiple form in some cases?
Yeah, so I mean, the model result I showed there was for a pure slope-oriented, perfectly flat slope oriented with the wind, which was driven by a perfectly oriented wind and so on. So that's incredibly idealised. In a real situation where you've got, different vegetation densities, you have slopes sort of meandering around, your winds are going to be meandering around, you will get multiple multiple vortices, I would say, almost definitely.
Thank you.
The slope driven by this will be very intermittent as well. It'll take faster runs and perhaps stop and then go again. So, yeah.
Thank you.
Great. Any further questions? Okay, well that appears to be it for the questions. So thanks for your time today, everyone, and again thanks to Valerie and Jason for their time in preparing their presentation and presenting today.
Yeah, no worries. Thank you.
Pleasure. Yeah.